This problem appears on the 2019 physics questionnaire of the qualifying examinations for applicants for Japanese government or MEXT scholarships for undergraduate students. The answer key and original questions are linked in the description.
Problem 2. Consider the circuit shown in Figure 2-1, consisting of a resistor R, a capacitor C, an inductor coil L, a switch S, and a battery with voltage V. At the beginning, the switch is in position B, and the capacitor is uncharged. Then, the switch is changed to position A. After having been in position A for a long time, the switch is changed to position C. Answer the following questions. In this problem, we talk about the charging and discharging of a series RC circuit. And so let us discuss some ideas related to that. We know that when a capacitor is charging in a series RC circuit, the current through that circuit is given by this equation. To obtain this equation, we need to solve some differential equation, and so we will not do it here. Now, if we talk about the current at the beginning of the charge, we just have to replace this with 0, t equals 0, which signifies the beginning of the charging. And we see that we get the expression of current which approaches V over R. And that means that the initial current through the circuit is V over R. And so if you look at the capacitor, or rather the resistor, the voltage across the resistor is IR from Ohm's law. And therefore, if we substitute V over R to I here, we obtain V, and this is therefore the initial voltage across the resistor. For the voltage across the capacitor, we apply Kirchhoff's law. It says that the total source voltage, which is V, must be equal to the sum of the voltages of the other elements. In this case, we have the voltage of R, the resistor, and the voltage of C, the capacitor. And because the voltage across the resistor is already V, the voltage across the capacitor must be 0. Now, when the capacitor is fully charged, we think of it as when t approaches infinity. And if we replace this with infinity here, we see that I approaches 0. Therefore, when the capacitor is fully charged, the current through the circuit is 0. And thus the voltage across the resistor, which is just IR, equals 0 because I is 0. And again, by Kirchhoff's law, we see that the voltage across the capacitor must be V. For the first question, we need to find the current I sub 0 through the resistor just after the switch is changed to position A. This corresponds to time equals t equals 0, and thus that corresponds to the current I equals V over R. And so this will be our answer. For the second problem, find the charge on the capacitor after having been in position A for a long time. This corresponds to the condition when t approaches infinity, and we see that the voltage across the capacitor at that time is V. And we know that the charge across a capacitor, or the charge on the capacitor, Q, is equal to just the voltage across it times the capacitance. And since the voltage across it is V, we know that the charge across it is CV. For the next problem, we talk about the discharging of a capacitor in a series RC circuit. We recall that the current through the circuit when it is discharging is given by this equation. And we notice that this is just the negative of the current when charging. The values here do not change. It is just the direction of the current. And here, time t equals 0 is taken to be the time when the discharging begins. Problem 3 asks us to find the joule heat generated in the resistor by the time the capacitor is fully charged. In other words, it is asking us to find the total amount of energy dissipated by the resistor from time t equals 0 when the charging begins up to the time t equals or approaches infinity. So what is the total amount of energy dissipated during the process? We first notice that at any time t from the start of the charging, the heat power dissipated by the resistor is given by this expression. So, for example, at time t equals 1, the power dissipated by the resistor is I of 1, and you square it, multiply it by R. So this is the power. To get the energy, we get the integral from 0 to infinity of this expression. However, we also notice that the current is just this current of charging is just the negative of the current at time t from the start of the discharging. So that is what we have here. The current during charging is just the negative of the current when discharging. And so the powers are also the same. And therefore, the total heat generated during charging equals the total heat generated during discharging. That is because this expression is the same as this in absolute value, and so when we substitute it here and we do the integral, they should give us the same value. However, we also know that the total heat generated during discharging equals the total energy stored in the capacitor. That is because the capacitor is the only source of energy during discharging. And we already know the total amount of energy in that capacitor, and that is 1/2 CV squared. And therefore, this is our answer. For the next two problems, we are asked regarding the LC circuit here on the right. So let us recall the current through the LC circuit, the series LC circuit. It is given by this equation. Here, the omega is just 1 over LC, the square root of that expression. And Q sub 0 is the initial charge in the capacitor here. Question 4. At time t equals 0, the switch is moved from position A to position C. How does the current I sub L, which flows into the inductor coil, change as a function of time? Find one appropriate graph in figure 2-2. We notice that the current through the circuit is this expression. It could either be a sine or a cosine curve, because the phase here could be pi over 2, and that gives us a cosine curve. Therefore, the only choices we have are D and C. However, we notice that the initial current through the inductor is actually 0. And thus, between C and D, we have this as our answer. For the final question, we need to find the maximum value of I sub L. That means we need to find the maximum value of this expression here. And we notice that this is a sine function. Therefore, the maximum value of this is just the absolute value of the coefficient of the sine function, because the maximum value of the sine function is just 1. And so we just need to find the absolute value of negative omega Q sub O. We know that omega is 1 over LC from here, and Q sub O is just the initial charge in the capacitor, which is given by the capacitance times the initial voltage in the capacitor. But the initial voltage of the capacitor is V because it is fully charged from when the switch was at position A. And therefore, we obtain this equation here. And the C's cancel, and the VO is replaced with V. This is the answer.
If you learned something new today, please help my channel by clicking the subscribe button and the bell for the notifications. See ya!